Thank you, Victor. I was not prepared for those super kind words at the start. So I'm a little bit, I'm feeling very honored. I've been looking forward to this day and to presenting my keynote paper on bridging knowledge between old and new energy projects for more than 2.5 years. And I must admit, it feels a little bit surreal to be standing here finally and seeing you all in 3D. While preparing for my presentation, I've noticed two things that I would like to share with you. First one was my memory is definitely not what it used to be, because I honestly had to go back and read and reread the paper before I could decide on what I wanted to talk to you about here today. And secondly, I can't actually remember the last time I stood together with so many people in a room, including yesterday, of course. Forget about actually delivering a lecture or a presentation in front of such an audience. So I feel totally out of place and out of practice, but please bear with me and I'll do my best. So after rereading and some contemplation, I decided to narrow down my presentation for today to 3 topics. And I just need to duplicate the screen here just a sec. So 3 topics. First one is enhanced cone penetrometer testing, which is a method that we developed for doing cost-efficient and time-efficient site characterization at our offshore wind farm developments. Second topic I would like to then cover is jacking trials, which is offshore plate load testing, or giant CPT as we have called it in some other publications since my keynote was published, which is again a very useful technique for optimizing site investigation and foundation design. Sometimes it's just not sufficient to do CPT testing or onshore laboratory testing. It's actually really important to understand the large-scale strength of the material in situ. And the third topic I would like to cover is the Rødby pile tests, which a large part of the paper is dedicated to. These are onshore pile load tests that we did, initially with the objective to understand better the pile installation behavior and to reduce the pile installation resistance. But then we utilized an external shoe on those piles, and it led to some concern about the lateral stiffness of the actual piles eventually. So we ended up doing some lateral load tests. And these were done in very high-strength clay conditions. The motivation for all of these initiatives was quite different, but they were all responding to a need that we saw in our offshore wind development portfolio. And all of them basically built on the experience we have from the old energy side of our business in Equinor. In the paper, there are more examples covered, but today I'll focus on these 3 topics. So starting off with enhanced CPTs, or enhanced cone penetrometer testing, I would like to tell the story here a little bit backwards, instead of actually telling you about the development of the tool and what we achieved and how we achieved it. I would like to start with what we did as what I run as a mini prediction event back in OSIF, Offshore Site Investigation Forum, in 2019. OSIF back then was attended by an audience of more than 20 highly experienced engineers, and I'm very happy to see quite a few of them in the auditorium here today again. And this audience was provided with the soil descriptions you see here in this table. So as you can see, it's an interbedded soil profile with quite dense sand layers and medium to high strength clay layers, with CPT cone resistance peaking at 110 or 80 megapascals. So the audience was then asked the question: if you took the biggest seabed CPT rig that you can get on the market today, when do you think, at what depth do you think it would refuse? Some thought that there's a peak of 110 megapascals at 10.8 meters. That in itself could be sufficient to for the rig to reach refusal, especially since the rods wouldn't have that much support further up. Others thought they were a little bit more daring, and then they thought, okay, we can get through that small peak if it's a relatively thin layer and penetrate through the clay layer underneath, but it would definitely reach stop at the very dense sand layer below 34.4 meters. I afterwards showed this CPT plot, which basically shows that you can see the cursor. The cone was continuously run down to 45 meters, going through the peak just over 100 MPa here at 10.8 meters, and through the relatively strong clay layer you see here, and then actually also through the 80 megapascal very dense sand layer here, again underlying layers. And we actually regret a little bit because 45 meters was the target depth that we gave the contractor. So we can't really call it a refusal. They might have been able to push even further. So how did we achieve that? First of all, well, this was through collaboration with one of our contractors, and it involved a lot of trial and error offshore. But one of the things that we introduced was lubrication along the CPT rods. So, and by that, actually, what I mean is in the ISO, there's an opening for using a friction cutter or friction reducer about 400 millimeters behind the con tip. So we had that, and just around that, we also started injecting some seawater. So that reduced the friction significantly. And on the plot here, you actually see 3 CPTs, which were with the blue traces, 3 standard CPTs, and you see the thrust capacity or the thrust increasing with the penetration depth due to frictional buildup with penetration. Whereas when we introduced the rod lubrication, you see the black trace here, you don't get the same frictional buildup with penetration. And actually, as it turns out, your thrust capacity becomes quite proportional to your tip resistance. The second thing that we then introduced was because the rod lubrication didn't take away the problem of getting through some thin, dense sand layers. So we also wanted to break that one. And the way we did that was, again, through water injection, but at this time at the cone tip. And we only really use that when we encounter some sand layers over 100 MPa. But you see the schematic here. So this was not at the face of the cone, but just behind the cone tip, and only some minute amounts of water were injected. And that was sufficient to mobilize the sand, and actually through these channels, the sand could be transported away. And we did this work together in a close collaboration with the Danish Geotechnical Institute. Again, on the plot here, in red, you see a standard CPT, which refused just below 20 meters. And then if you look at the black line, the black trace, you see it was possible to penetrate through that sand layer into the underlying clay layer and significantly further, again, stopping the test at 45 meters. Why is that important? When it comes to offshore wind developments, we need to have turbine-specific information, or it's a great advantage for foundation design to have turbine location-specific information. However, obviously we would like to use the biggest turbines, and they're not necessarily available when we need to finalize our design. And to do a geotechnical soil investigation and then onshore laboratory testing, it all takes a very long time. So doing a CPT is significantly faster than doing a borehole, so there's no way we can actually do a proper borehole campaign when the turbine layout is available. But with this method, we can basically do a reconnaissance soil investigation, do the onshore lab testing, and afterwards do the location-specific investigation relatively close right after the layout is available. And further details of this, how the enhanced CPT system development has been published by Gulin Yetginer of Equinor at the CPT 22 conference from Italy this year. At the end, enhanced CPTs were used at more than 100 locations at Dogger Bank and elsewhere. This is basically what we based the final foundation design on at Dogger Bank. Which brings me to my second topic, offshore plate load testing or jacking trials, which we also conducted out on Dogger Bank. As I said, sometimes it's not sufficient just to do CPTs onshore lab testing. It's really important to understand the in-situ material. But so at the time the paper was published, and what is covered in the paper is the jacking trials that we did in 2017 with the Sea Challenger, which is the jack-up rig you see here on the left-hand side. But shortly, actually, after I submitted the keynote paper, I was lucky enough to also join the campaign offshore with the Woluwan, which is a jack-up rig owned and operated by Jan de Nul. So what I will present today is actually some of the newer results from the 2020 campaign. But before I would like to, so you can understand the motivation here a little bit better, I would like to say a few more words about Dogger Bank. So Dogger Bank is one of the biggest offshore wind farm development in the world. The whole area covers close to 9,000 square kilometers. It's approximately 150 kilometers of the UK coast in the middle of the North Sea, but it's actually quite a shallow bank. So the water depths are about 18 to 63 meters. Currently, the plan is to develop it with 277 turbines, all founded on monopile foundations. And just to illustrate the size of the area, the three projects where we are partners, Dogger Bank A, B, and C, if you superimpose their layouts over Greater London area, you see that it covers all of it. The geology out on Dogger Bank is really complicated. So these are not classic sedimented soils. It's a highly deformed glacial sill created basically as the ice sheets from Britain and Scandinavia collided and oscillated across the wider area. And they have also been exposed to a lot of cyclic processes as well as extended periods with permafrost. So standard empirical correlations that we can normally rely on, we can't really rely on those for Dogger Bank. On the right-hand side here you see the cone factor plotted against depth. And this is basically only the high-quality onshore laboratory test data. And the scatter is basically quite astonishing. The problem with that is if we were to use the conventional approaches of foundation design, and we had to design the piles according to lower bound design curves, we would basically not be able to install them, because then you would also need to take into account the higher end of the shear strength, and you would end up with a huge dryability risk. So the most important thing actually is the scatter is one thing, but the wide range of the design profiles would be unsustainable. Similarly, just to, again, illustrate some of the challenges, here on the left-hand side you have the shear strength from high-quality anisotropically consolidated fracture compression tests from 30 sites worldwide plotted against pre-consolidation stress. This is work and a database which is basically on the grid that has presented previously. And on the right-hand side you have the same data plotted with the same scale and everything for Dogger Bank, which basically looks like a gunshot. Don, when he presents this database, he normally talks about that the soil remembers the highest, what has happened in its past, the highest pre-consolidation stresses it has seen, so that soil has a memory. But obviously, Dogger Bank doesn't seem to apply to Dogger Bank, and then we talk about loss of memory. So it was mainly these challenges that led to coming up with the jacking trials. As I said, there were 2 campaigns performed, 5 locations tested in 2017, and then another 6 locations tested in 2020. At some of the locations, we actually managed to push the spud cans of the jackup, which were about 110 square meters in area, to about 20 meters below the mudline. And the motivation here was we realized that shallow failure patterns for a spud can of this size and a large monopile are quite similar, and they mobilize similar soil volumes as well, making the NKT, operational NKT back calculated from this data quite relevant. So it's basically doing like a full-scale test. And here is, I would like to show you the leg penetration curve from one of the locations. So on the left is the preload that was applied and the spud can penetration with depth. The different colors here indicate the 4 legs of the jackup that we pushed into the soil. The black dots are the load measured and the penetration measured at the end of each load increment that was applied. And then this data was basically back analyzed using the ISSFOG conventional bearing capacity calculations, as well as finite element analyses. And in the middle, you see the best estimate fit to the cone penetrometer profile. And combining these 2 data, we were able to back calculate a cone factor with a much narrower range. In the paper, I've actually written that we ended up with 19 to 21, and that was the result of the back calculations. But when it comes to the final design stage, we decided to open that up a little bit due to the uncertainty and variability across the site. What's interesting is Marsland, back in 1970, when he was doing plate load testing in London clay, he noted there was a negative scale effect with bearing capacity increasing, whereas at Dogger Bank we've actually noted a clear positive scale effect. And this has something to do with, obviously, distribution and size of fissures. And that's further discussed in the keynote paper. We also did some cyclic testing, again using the spud can, just preloading and unloading and reloading. that also led to some interesting results, which we haven't published yet. And more details on this, again, has been published in the CPT22 paper. That's, you see the reference for at the bottom here. Then I would like to move on to the last part of my presentation, which also a large part of the paper is dedicated to, and that's the pile test we did out on Robu. Also large-scale testing. The motivation for Robu pile test was, this is not related to Dogger Bank at all. It was the Dudgeon wind farm when we were designing the foundations. It was we found out the Swarty Bank formation was actually present within the foundation depth. Others have talked about Swarty Bank yesterday. It's quite a challenging material, really old, over-consolidated clay formation with undrained shear strengths in the range of 500 to 1,000 kPa. So where you see the blue and the green shading on the plot on the right-hand side, that's where Swarty Bank was below, approximately 15 to 20 meters below the seabed. So that meant we had about 12 locations where we would encounter Swarty Bank with some concern about whether we would be able to actually install the monopiles to target depth or not. This led to questions about, okay, well, how can we reduce the driving resistance? We considered different options, low frictional coating. Obviously, we could have had as a backup that we would drill out the pile plug, but we didn't want to take that risk to begin with. But at the end, we decided, okay, external shoe should actually help. But we didn't really find sufficient material in the literature to justify a design based on what had been published previously. So we thought this is a good case for doing physical testing, onshore pile load tests. So the main objective was actually reducing the driving resistance, but at the end we also ended up using, being concerned about the lateral response if the oversized hole that we would create could potentially influence the lateral response of the piles. We were lucky enough to find a site in Robu, which is in Denmark, with quite similar soil conditions to the conditions we expected to see offshore. Here you see the cone penetrometer profile on the left-hand side and the associated undrained strength. And the black lines represent the best estimate profiles we've used in the back analysis of the data. We installed 6 different piles. One with no shoe at all, no external shoe and no internal shoe. One pile with only internal shoe. And 3 with different varying thicknesses of the external shoe, as well as one last pile where we also experimented with the length of the shoe, if that made any difference. We had some additional steel rings with us to modify the shoe if needed on site, but that was not needed at the end. The piles were equipped with strain gauges and accelerometers, and we also obviously performed PDA measurements. Here you see on the picture you see one of the piles in production. So the piles were 10 meters in length and they were installed to 7.5 meters below ground level with an outer diameter of 1.22 meters. So of course 1.2 meters sounds quite small when we talk about monopiles of 8, 9, 10 meters in diameter, but it is actually quite big enough to fit 2 happy geotechnical engineers inside the pile. Here is some of the results from the site. This is the dryability, the blow counts that we actually measured when we installed the 6 piles. In dashed lines on the right-hand side, you see the measured data, and the solid lines represent the back calculations. So obviously this is quite a bit of material to go through, and it's a busy slide, I apologize for that, but details are given in the paper. But what we did is, in the upper table, is basically the back analysis normalized with pile 1, which didn't have any shoes, not internal, not external. And the lower table is using pile 2 with just the internal shoe, so only focusing on the external skin friction reduction. We revised the SRD profiles using wave equation analyses. And then based on the PDA data and using CapWeb, we interpreted the driving results and evaluated skin friction distribution, which is what we used in the FE analyses. Based on the work, and it was at the end, you see the numbers are quite variable depending on what you believe in, and we can all basically it's hard to get two geotechnical engineers to agree on things. So we ended up taking an average of these, and obviously if we erred on the conservative side and scaling up the FE model, we ended up having an internal-external driving shear of 20 millimeters in size for the actual piles that we installed out on dudgeon, which we approximated to give us 25% reduction of the total skin friction. At the end, dudgeon is up and running. This was a while back. The rotary tests were performed in 2014, and all piles have basically been successfully installed to depth. After the installation, as I said, we were worried about the lateral response of the piles. So after leaving the piles in the ground for a couple of days, we tested them, pulling them towards each other. You see the load steps shown here on the right-hand side. And then, and here is basically comparing the observations, the measured data from those tests with the predictions which are out there. So again, I'll try to talk you slowly through what's on this busy plot. In gray in the background, you have the measured data from the tests. In the magenta line, which gives a quite soft prediction, is the current API matlock method. In blue, the dash line in blue, as well, and the dash green line, the blue one is the updated API PY model without the tension gap. And the dash green line is the PISA model without site-specific calibration. So those are really good in capturing the initial stiffness, but then they are obviously, or they are overestimating the capacity at larger displacements, which is to be accepted without site-specific calibration. The solid line is the updated ISO curves with gap, and that gives a slightly better match than the existing API lines, but it does not capture the initial stiffness. In black, we have the finite element results, which have been calibrated, and we also did the Redwind macro foundation model is also shown here in red with dash lines, and that gives an excellent prediction, but that's because it had site-specific calibration. What was most important for us was really that there was no significant difference between the piles with or without the shoe. And we were very happy to have that confirmation. Afterwards, so those were the tests which were done with an L/D ratio of 6.1 with penetration of 7.5 meters. But afterwards, we also thought, well, 7.5 L/D, that's not really that representative of monopiles offshore. So we then, before we demobilized the site, we actually excavated around 2 of these piles and did also some lateral load tests with an L/D of 3.5. The results and discussion of these obviously are presented in the paper, but they confirm the observations that we had from the L/D of 6.1. So based on this, it was possible to conclude feasibility of monopiles at all of the turbine locations on dudgeon, which meant that we didn't have to count or have jackets as a backup foundation option, resulting in a lot of cost savings. So to conclude, and I would like to just recap and share some final reflections. So in the presentation today, there are many more examples of this in the paper, but in the presentation today, I'll focus on 3 examples. And to me, they all represent examples of developments building on our and the industry's experience from oil and gas business. If it wasn't for the fact that a mature soil investigation industry was already available, we wouldn't have been able to push the CPTs to their boundaries and beyond and come up with the enhanced CPTs. And if it wasn't for the experience that we have, the picture you see here on the right-hand side, we have with field testing out on Gullfaks and elsewhere in the 80s and afterwards, we may not have actually performed the review tests or the jacking trials for that matter. And if it wasn't for the existing guidelines and all the model testing that was performed for modeling jack-up behavior and leg penetration analysis, we wouldn't have been able to extract the full value out of the jacking trials and compare failure patterns. And of course, I didn't mention floating wind today, but this is a little bit more, there's a bit more detail in the paper. But of course, especially floating wind developments are also very much strongly building on the experience from old energy. Similar experience transfer is now happening basically every day through us here in the audience. I see many good colleagues when I look around the room with whom I used to discuss oil and gas projects and work together on oil and gas projects in the past. And I'm very happy to note that today we're actually discussing offshore wind and other types of projects. However, sometimes I also have conversations with, in particular, some younger engineers, younger colleagues, which remind me of a particular scene from Monty Python that I hope at least some of you in the audience will still remember. And if you don't remember the scene, I'm not going to read it or try to make a point out of it. So I hope I managed to bring some peace to the discussions with my presentation and the paper. And last but not least, I would like to, of course, acknowledge our partners for giving us supporting the work, as well as giving us permission to publish. And my co-author, Toringe Hjelta, who has been the inspiration and originator of a lot of the ideas presented in the paper. Thank you very much for your attention.